Everyone. Yeah, let me take where I left off. So very quick recap. So first day we defined Markov chains, and then I stated three questions. So we were discussing the first question, which is of the long-term behavior of a Markov chain. So what we were doing yesterday was we have this Markov chain on a state space, which is with a finite state space. So the whole, I forgot to mention. So one can ask these questions for countable state space, but the matrix theory methods that I'm telling will apply to finite ones. So for the infinite ones, there are other ways of doing it, or maybe there are limiting procedures also from the finite one, but we will stick to finite state space, which is already quite interesting. So we have a finite state space Markov chain with a transition matrix P. And the question is, what happens after a long time? What is the distribution of where the Markov chain will be? If you start at I, after a long time, what are the probabilities to be in different states? And the first thing we noticed last time was that this has very close connection to matrix multiplication, namely the probability that xt is j, given that x naught was I, at time 0 it was at I, the probability that it is at j at time t is given by the entries of the matrix p raised to the power t. T here is a natural number, 1, 2, 3, 4, etc. So you just need to solve the problem of the limiting values of this, if at all there are limits, what we need to understand is how to raise the matrix given to a large power and then look at the entries of it. Okay, and the conclusion is that under some conditions that this limit exists and depends only on j, not on I. The starting location gets forgotten and there is a certain probabilities at to be in various states. Okay, so that is the conclusion I came to, that under some conditions p to the t ij converges to pi j for all I and j, and the limit does not depend on I. This pi j, so what are these, how did we come to this? So, well, the problem of raising a matrix to a high power is a very important one, not only for Markov chains, but other situations. One of the simple situations where that happens is if we take P to be xd x inverse. If P is diagonalizable, then raising P to a power becomes easy because it is x times d to the power t x inverse, and d being diagonal, we can raise it to a large power, any power we want. Now, what happens to this thing when we take limit as t goes to infinity? Fact is that all the so P being a matrix such that all the entries are non-negative and the row sums are 1, what we saw is that 1 is an eigenvalue. For example, P applied to the vector 1, 1, 1, 1, 1 gives the same. So 1 is an eigenvalue and this is an eigenvector. The constant vector 1 is an eigenvector with eigenvalue 1. And all other eigenvalues have absolute value less than equal to 1. So they are all in the unit disk, closed unit disk in the complex plane. That is a fact, true in general. Now, the point is when we want to take a limit of this, it helps if one eigenvalue, which is 1, and all other eigenvalues have absolute value less than 1. Okay, this is not always true. So let me give example where this is not always true. Last time I did not discuss that point. So let me just say that now. To start with, let me just point out that this assumption is not always valid. So this idea that P has eigenvalue, so need not be true. Okay. What is an example? Let's Let me give two examples in a two-state Markov chain. We'll come back to these examples and say what is wrong about them. So you take P equal to 1001, or the second case P is 0110. The first Markov, both are very simple Markov chains. There are two states. In the first Markov chain, what happens is whatever state you are in, you just stay there forever. If you start in state A, you stay you go from A to A and B to B all the time. Okay, in the second one, you alternate. You always go from A to B and B to A. So you keep doing this. But the point is, okay, sorry, this is a here there are. So here the problem is that one has multiplicity 2. The eigenvalue 1 has multiplicities 2. In fact, both eigenvalues are 1 and it has multiplicity 2. Here, the eigenvalues are 1 and minus 1. Now, it is true that 1 is a simple eigenvalue, but the other eigenvalue also has absolute value 1. Both have absolute value equal to 1. And these two are in fact problematic things for the conclusion also. It's not that just the assumption fails, the conclusion also fails. What happens if a Markov chain runs like this for a long time? Okay. So take both cases. Maybe I should write it somewhere else. Okay, where did I? Both the conclusion fails in both cases. For example, here what happens to p to the power t will always be p. That means if you start at a, you will remain at a, and if you start at b, you will remain at b. So the initial condition does not get forgotten. Okay, you always stay in the initial condition in a trivial sense. So initial condition does not get forgotten here. In that sense, the conclusion fails. In the second case, what happens is alternate times, if you start at A, then at even times you are at B and at odd times you are at A. So there is no limit to P to the power Tij. Okay, maybe I'll come back to that, but both conclusion and assumptions fail here. So these assumptions are to some extent important. Well, that is what I was investigating last time, and I will repeat, I will now start from that point that this one eigenvalue being 1, so the, 1 being a simple eigenvalue and other eigenvalues having absolute value less than 1 is important because without that, these two examples show that the conclusions fail. But the other assumption about the diagonalizability is not important. Okay, that I began saying by the Jordan decomposition, but maybe let me go on to a new page and start. In case I lost you last time, I'll just
Sir, why the conclusion fail in the first case? Because limit exists.
limit exists, but it depends on the starting point, right? So if you see, one nice thing is if the limit here, the conclusion that we got under these assumptions, which I am going to now do under the more general assumption, dropping this diagonalizability assumption, okay, is that the p to the t, the conclusion was, where is it? P to the t ij converges to pi j, which does not depend on I. Okay, in the first case, when P is the 1001 matrix, P to the T 1 comma 1 converges to 1. Okay, but P to the T 2 comma 1 converges to 0. So it depends on I also. That's the difference. So that's the thing. Is okay?
Okay, sir.
Yeah. So the limit exists, but depends also on the starting location, which is in a way not good because I mean after a long time we hope that the initial state is forgotten. That's what I would like. Now, one can study, yeah. So let me continue now here. Sort of, I'll repeat a little bit, but with fewer assumptions. So now let's repeat, sort of. So S is a finite state space. So when I need, the size of S will be N. And P is a transition matrix on. And X is my Markov chain. Markov chain with transition P. And the main thing that we have seen from which everything is coming is that probability that xt equal to j, given that x naught equal to I, is the ij entry of p raised to the power of t. Okay. So now let me weaken the assumptions that I am making. So first, so the assumptions that I make are okay. Let me also write down the other fact that we already noticed, that 1 is always an eigenvalue. Okay, and then recall eigenvalues of p are of absolute value less than equal to 1, and 1 is an eigenvalue. Namely, p applied to the constant vector 1 gives you 1 times that vector. So this is true in general. Now the assumption that I am going to make is exactly that assumption 2. I will drop assumption 1, that assume that lambda 1 equal to 1 is simple. So the eigenvalues, I am calling them lambda 1, lambda 2 up to lambda n. Okay, so they are repeated possibly. So a simple, and all other eigenvalues are less than 1 for all j equals 2 up to n. So I will drop the diagonalizability assumption. Okay, but suppose I make this assumption again. I will suppose this assumption holds true. Then how can we, then again I want to give the same conclusion as before, except that I cannot. Last time what I used was the diagonalizability, so I got p as dx x dx inverse, and now I cannot do that because I cannot, I don't know whether I can diagonalize, but what I will use is the Jordan canonical form. Okay, so the Jordan canonical form tells us that okay, so the Jordan canonical form what it says is that we can write P as X. Now it's not anymore a diagonal matrix, so let's call it maybe J X inverse. Okay, where J is going to be of this form. The first eigenvalue I will make to be 1. So that will be a single block. Okay. So that will be a single block, and all others will be Jordan blocks of size 1 or more. For example, here I may have some eigenvalue, let's call it lambda 2. Okay, this lambda 2 slightly should be differentiated from that, because here, okay, so maybe some eigenvalue will be having a Jordan block of size 2 or 3, let's say. It could look like this. So that is a Jordan block. And then all these will be 0. Everything else here, which I am not writing, are all 0. Here maybe lambda 3 is a Jordan block of size 2, and so on. Okay, actually it doesn't matter what the size is. Maybe if the matrix was diagonalizable, all of these would have size 1, but we are not assuming that. We are just, we don't care. Only important thing is that 1 has eigenvalue, 1 is a single Jordan block and all others are less than 1. Okay, and x is, what is x? Only thing about x that I need is that the first entry, the first column is going to be 1 1 1 1 1. and then whatever else on the rest of it. It's invertible, but the first column I can take it to be the eigenvector corresponding to 1. These Jordan blocks, if you remember, the point is that arithmetic multiplicity is not always equal to geometric multiplicity. So each Jordan block has only geometric contributes. So for example, if lambda 2 itself can, this lambda 3 is not same as this lambda 3. Lambda 2 can occur in two Jordan blocks. However many Jordan blocks it occurs in, that is the geometric multiplicity of lambda 2. And so any eigenvalue, that's how it is. So for each Jordan block, we get one eigenvector. Okay. So, but for one, there is an eigenvector, the constant vector 1. That is what we assume. So once we have this is very general. The Jordan canonical form is true for every matrix. And because of this, immediately we get that p raised to the power t is x, and then j raised to the power t x inverse. Okay. Now, what is x j raised to the power t? Since it's a block diagonal form, all of these matrices will get raised to the power. So let's just do a small calculation on the side. Let me just do a small calculation on the side. What happens to a Jordan block when you raise it to a high power? So let's just take a Jordan block like this, lambda, some lambda, 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 and let's say 1, comma 1 and 0. So what happens when you raise it to the power 2? Square will give us the, what you will see is that, so this becomes, the diagonals will be lambda square, lambda square, lambda square, and then on the off diagonal you get some stuff. Okay. What do you get actually? So maybe it is, yeah. So this entry will have, yeah, so this is first column, so this will have 2 lambda, I think. Okay, so lambda lambda, maybe I just do it on MATLAB, so it is just easier, so we can just see what it is like. Okay. uh, Mathematica, where was, 1 second, so that will be just easier for me to show. Okay, so here is Mathematica. No, okay, this one. Okay. So just let's take a Jordan block and then see what the power of it will look like. So that is just a, I mean, we can do it by hand, but okay, what is happening here? Okay, so let's take J to be a matrix like, okay, so hold on. So maybe it's not working. Working. Okay, so let's call it X 1 0 0. I'm taking a 4 by 4 Jordan block, 0 X 1 0 and 0 0 x 1, and the last is 0 0 0 x. Okay, so let's take this. So this is a Jordan form, so let's raise it to a power of j to 2. Okay, so let's just write it in matrix form. So when you raise it to a power 2, you see x square, of course, on the diagonal, and here you have some 2x. So let's raise it to some higher powers. So 3. What happens is you get some x's here also. This is still 1, but when you raise it to 4th power, you see everywhere you will have some x's. Okay. And so when you raise it to much higher power, let's raise it to power 10. So on the diagonal, we have x power 10, but everywhere else also we will have powers of x, okay, with some coefficients. One has to be slightly careful about what the coefficients are. They matter to some extent because the coefficients are becoming larger. But what is easy to check is that this thing converges to 0. The whole thing will converge to 0 when x is less than 1. Sorry, when absolute value of x is less than 1, these things will converge to 0. Okay, so that is the only point that I want to use here. And so just going back, so that is something you can check, and I will just leave that here. So the point is, when you raise j raised to the power t, each of the Jordan blocks gets raised to the power t, and as t goes to infinity, everything goes to 0, and this converges to the matrix X, and then the matrix with 1 in the 1 entry, and everything else is 0. X inverse. So which means that p to the power t, the I comma j entry, converges to pi j, which is pi j is just the x inverse entry. So what is the I comma j entry of this? It will be xi1 xj. It is actually the ij entry is xi comma 1 x1 x inverse 1 comma j. So xi comma 1 is 1, so it will be x inverse 1 comma j. Okay, so that is all it is. So for all ij, this happens. So we got the same conclusion as before without assuming diagonalizability. That's all. Just using the Jordan canonical form. Okay, and this conclusion is that it doesn't depend on j. So this does not depend on I. Okay, does not depend on that. And what is x inverse? Okay, we will come back to what is x inverse 1j later. So now that more or less completes the answer to the question that what is the long-term behavior, provided we have this assumption that lambda 1 is simple and all other eigenvalues are of absolute value less than 1, then the conclusion is p to the t ij converges to pi j for some numbers pi j. Okay, but what one more step we will take, and this is where we mentioned Perron-Frobenius theorem, one of you mentioned it, and we will bring it in. The assumption here is a tad involved. I mean, in the sense we have to actually find the eigenvalues of P and check whether the eigenvalue 1 is simple or not, and whether all eigenvalues are less than 1 in absolute value. Can we just look at a matrix P and tell whether or not this is the case? Okay, so that is where the Perron-Frobenius will come in. An easy way to check the assumption that lambda 1 is 1 and lambda j is less than 1 for all j greater than equal to 2. Okay, so this easy way is the Perron-Frobenius theorem, but it also fits in nicely with something meaningful in the case of, as we saw, this conclusion is not always true, and it is this assumption is also, it fails. So it fails for these two examples. Okay. So what are the general properties captured in those examples which we can exclude so that we will have this assumption? So, okay. So these are the two properties. So one is called, so let's make two definitions. So a Markov chain, which is basically, or its transition matrix, P is irreducible. So what does it mean? Irreducible if, okay, let me write in words, one can go from any state to any other state. Okay, if one can go from any state to any other state. For example, if you look at this two-state Markov chain, this first one, 1001, if you start in the first state, you cannot go to the second state at all. You will always stay in the same state. Okay, so Markov chain is said to be irreducible if you can go from any state to any other state. So this is a very important concept and meaningful, because I mean in all natural examples we think of this should be true, but it need not be always true. So mathematically what this means is that is for all I and j in S, okay, there exists T such that P to the T I comma j is positive. That means you give me any two states, there is a time. I mean, so what does it mean? You can go from any state to any other state. Maybe you can go in 10 steps, you can go in 20 steps or 150 steps. But there is a t finite such that there is a positive probability to go in that many steps. P to the Tij, you remember, is the probability to go from I to j in t steps. So this says that there is a positive probability, and this t can depend on I and j. Okay, so this t can depend on I and j. So how, for example, you take the second example or any this example. Okay, so A and B are the two states. So here to go from A to A, it's only possible in even number of steps. From A to B, you can go in one step. From A to A, it takes two steps. Okay, so that's what I mean by the time can depend on the number. I mean the number of steps we need can depend on the states. That's okay. So but that is what is called irreducible. Really speaking, when I define Markov chain, you are thinking of irreducible. For example, in random walks and graphs, irreducible just means the graph is connected. Okay, so if the graph is connected, then the Markov chain is irreducible. So let me just write that as an example to keep in mind. Example: simple random walk on a graph is irreducible if and only if it is connected. If the graph is connected. Okay, if the graph is connected, whatever two states vertices you give, there is a path from this vertex to that vertex. Surely you can go to from here to there with a positive probability, right? I mean, if you have a path of length 5, you can take those steps with some probabilities, positive probabilities, and get from I to j. So this is one of the important properties of a Markov chain. And there is a second one. So you see that this second one here, this is not irreducible. So this is indeed irreducible, because you can go from first state to second state in one step. You can also go from first state to first state in two steps. Second property, what is it that the second one lacks, but the first one, right? So second one also is problematic in some way. So that is a Markov chain is aperiodic. Okay. So this is another property called aperiodic if for any, okay, or let's say for some, it will be the same as for any. I will Okay, actually, okay. Now let me just say for any I. For any I in S, what we aperiodic means the following thing. Okay, let me tell you what is periodic. First, let me just give an example and say what is periodic and then write the definition. So if you imagine random walk on this graph, okay, this is slightly less trivial than the other one. So that's why I'm giving this A, B, C, and D. And let us say x not equal to A. So if we run the Markov chain for 1000 steps, then I know that at the 1000 step, although it's hard to predict what will happen, I know it will be either in B or D because, in A or C. After even number of steps, it will be in A or C, and after odd number of steps, it will be in B or D. Because if you start at A, odd step you will be either in B or D, and next step you will be in A or C. So there are these two pieces. So it will whether you are in AC or in BD depends on the parity of the step. So if that is a case of periodicity, so this is periodic. Okay, there is a periodicity that in you can only come back in an even number of steps. So what is not periodic then? Not periodic means it doesn't really mean you can come back in any number of steps. Maybe not because it may take a few steps to come back. So what it means is if you look at all the times when you can come back, look at all t greater than equal to 1 such that you can come back in P, not ij, p to the t. How many? So probability that you come back in I steps exactly, in t steps is positive. We look at all the times at which you can come back. For example, in this graph, if you look at A, state I is A, then the times at which you can come back are even numbers 2, 4, 6, 8, and so on. Okay. So, but we don't want that situation. We want that the GCD of this set should be 1. So that's not the case there because you can come only in even steps. The GCD would be 2. So Markov chain is aperiodic if this GCD is 1. So how can I make this aperiodic? For example, just a very simple way, or not simple, if I change it, it will become aperiodic. So for example, if I have a graph like this, and let's say you put another edge here. Okay, so this graph, this is aperiodic. Why is that? Let's take this state I, A. You can come back in 2 steps, right? So you can come back in 2 steps. So you can come back in 2 steps. So P square AA is positive. Because you can go from A to, let's say this is B, this is C, this is D. You can go to B, so you can go to A to B and back to A. But you can also come back in 3 steps. How? You can go from A to B, B to C, and C to A. Right? So if a graph has an odd cycle like this, then it will be necessarily aperiodic. The simple random walk will be aperiodic. So more generally, this is the definition of aperiodicity of a Markov chain. Okay, so this is another key property that is important. Now the problem with this other chain that I mentioned is that it is not aperiodic. This is periodic. This second chain, so I mentioned 2 chains which are problematic. So the second one is irreducible, but it is periodic. So the GCD of these numbers is period is 2. Meaning you can come back only in even number of steps. From A you go to B and then you come back to A. So these are the 2 problems is if the 2 problems are if it's not irreducible or not aperiodic. Now the key point that the theorem that, so going back, what was it I was up to? I wanted an easy way to check that Markov chain satisfies the assumption that 1 is a simple eigenvalue and other eigenvalues are less than 1 in absolute value. And the statement is, let me state that fact or theorem, whatever. So if a finite state space Markov chain is irreducible and aperiodic, then the assumptions are satisfied. First eigenvalue is 1 and all other eigenvalues are strictly less than 1 for all j greater than equal to 2. Okay. So it is much, so you don't need to actually compute the eigenvalues to check it. You just have to check that it is irreducible and aperiodic. Now, this is usually very easy to check. Okay. Irreducible, you see, for example, random walk on a graph is irreducible, means graph is connected. It is somewhat easy to check that a graph is connected. And aperiodic also is usually easy to check. Okay, if you have odd cycles, if you can usually come, well, not always, but you have to see if you can come back in 2 steps and 3 steps, then it is aperiodic. Or if you can come back in 8 steps and 9 steps, then it is aperiodic, like that. So it's not hard to check. This is much easier to check that the irreducibility and aperiodicity are easy to check. You don't need to do any computation of eigenvalues or anything. You just can look at the matrix and calculate this, check this. Okay, so that is the point. So this reduces the, so as a corollary that we get that for an irreducible and aperiodic finite state space Markov chain, p to the t I comma j converges to pi j for all I comma j in S. This is as t goes to infinity for some pi j's. They don't depend on I. That is the important thing. The initial state is forgotten and it converges. So this is the nice conclusion. So just irreducible and aperiodic ensures that this happens. Okay, this is the corollary. So we just need to explain why this fact is true and where does it come from. So Rajesh has already discussed the Perron-Frobenius theorem. So the proof is really Perron-Frobenius theorem. Okay. So what one can show from these two things. So I will just outline 2 steps. Maybe you have done it in, maybe Rajesh has in fact done this. So irreducible plus aperiodic implies that there exists some t, okay, such that if I raise p to the power t, all the entries are going to be strictly positive. For all I and j. So there is a power of the matrix which has strictly positive entries. Okay, this is you see, these examples are where it fails. So if I raise this to any power, you will get back the same. If you raise this to powers, you will either alternate between square will be this one and cube will be back, square will be this, cube will be back. Always there are 0 entries. But if the chain is irreducible and aperiodic, there is a power which has all entries strictly positive. Okay, so this I will leave you to check why. It's not completely obvious, but it is not super hard. So irreducible means almost irreducible would look like almost this is what I'm saying, but that's where the point I was emphasizing comes. Irreducible means for every pair of states, there is a power time such that p to the t ij is positive, but this time can depend on inj. Okay, for example, here in this two-state Markov chain, to go from A to B, you need powers to be power is has to be odd, and from A to A, power has to be even. But here we are saying there is one power for which all the entries are positive. For that, we also need aperiodicity. Okay, both irreducibility and aperiodicity together will ensure that. And then once you have that, you can apply the Perron-Frobenius theorem to this. So now you can apply Perron-Frobenius theorem to this power. So p to the t Perron-Frobenius says that see p to the t always has eigenvalue 1, right? That's the largest one. That's the row sums are 1. P to the t is also a transition matrix. It's the t-step transition matrix that the 1 is the okay, sorry. 1 is a simple eigenvalue of p to the power of t. And all other eigenvalues have absolute value less than 1. Okay, so the first form of Perron-Frobenius, sometimes it's also stated with irreducible. Maybe you did that, but if you just take the one for strictly positive entries, what it says is that you look at the eigenvalue of largest absolute value is in fact the positive number, which is the largest. So in this case, it is 1, and all other eigenvalues have absolute value strictly less than 1. But what are the eigenvalues of p to the t? Of p to the t are lambda 1 to the power t, which is 1, and lambda 2 to the power t up to lambda n to the power t, where lambda k are eigenvalues of p. So if the largest one is 1 and others are, so this implies that mod lambda j to the power t is less than 1 for all j greater than equal to 2, but that's same as lambda j is less than 2, less than 1 for all j greater than equal to. So this is the assumption. So there is one eigenvalue which is 1 and all other eigenvalues which are strictly less than 1 in absolute value. So irreducibility and aperiodicity implies by the Perron-Frobenius theorem this condition. And then we have this long-term behavior. Okay. So that completes what I wanted to say. I mean, I will go further and I will now discuss what is this limiting numbers and calculate that pi j, this limiting pi j's, what are they and how do we calculate it, that I will discuss. But this is a good stopping point to take questions if there are any.
Professor,
Yes, please.
can you explain periodicity once again?
Periodicity means that, yeah, so there is no, see, you can have a complicated Markov chain. Okay, so for example, take a Markov chain like this. So let me just write an example of a Markov chain here. So let's say a grid like this. So take a grid. It need not be square. I mean, some grid like this. Let's say the starting location is this one. the thing is, suppose can I tell where the Markov chain will be after 100 steps? If I ask that question, the point is there is some sort of information. Yes, it can, we can tell it cannot be anywhere. So we don't know where it will be. But what we can say is that it has to be in only these. After 100 steps, it can only be in either the starting point or these alternate ones. Okay. For example, if I color the vertices of this grid like in the chessboard, black and white, so I am marking all the black vertices, let us say. Okay. The thing is, always you move from a black vertex to what is not marked, let's call it white. You always move from black vertex to white vertex and white vertex to black vertex. So that means in even number of steps, if you started in a black vertex, after an even number of steps, you will be in a black vertex. So although I don't know, have any clue where it will be among these black vertices, I know that it cannot be at any of the white vertices. But after 101 steps, I know that it will be exactly in one of the white vertices and not in any of the black vertices. So this is periodicity. Periodicity is that it has this type of information. Even after a very long time, we retain some information of where it started because of this parity issue. Now, if only I had put one more edge, okay, if I had put just one more edge somewhere, okay, so let us say we put an edge like this. Now, this completely destroys the bipartite structure and you can come back. Now, I cannot say that after 100 steps I will be in black vertices because I can come here and then, sorry, this was the wrong one. Okay, sorry, I made a mistake. That is still bipartite. What I wanted to say was, let's say we put an edge like this. Okay. So now I cannot say such things. After 100 steps, what can happen is if I come to here, in one step, I can again go to black to black. That completely destroys this business that at even times I am at black and odd times I am at even. That's not anymore true. And that will destroy it. So that's what aperiodicity is. Okay, aperiodicity is that you don't have any such information, that you can only come back in even number of steps, or you can come back only in multiples of 3 or multiples of 4 and such things. You, after a while, you can come back in any number of steps. That's exactly what it really means. Okay, so I explained in a slightly different way, but so if you look at all the times when you can come back to the state I and take those times, there should be no common factor. That is what that if there is a common factor, that would, we will call it periodic. If it's no, there is no common factor, we call it aperiodic.
Okay, sir.
Okay. Any other questions?
Hello,
Okay.
sir.
Yes, please.
It's to do nothing with our like this won't affect our discussion. But you said the given Markov chain is of period 2, right?
Yeah, so this one, for example, this one
Yeah.
is period 2. Any bipart, if you take random walk on a bipartite graph, it will have period 2, because you can go only from, there are two parts, you can only go from white to black and so on, right?
So in terms of GCD, that's because the times form this set 2, 4, 6, 8, right?
Exactly, yes. You
So
can,
that would mean in a Markov chain, if there are this happens for two different eyes, we'll have suppose two different GCDs. A graph can be of, I mean, Markov chain could be
yeah,
of
let's
multiple
say
periods.
that's a very good point. Actually, I glossed over it. Okay, a periodic, really, the period depends on the state. It's a good point you are making. The period can depend on the state. But when the Markov chain is irreducible, you can check that all the periods have to be the same. It can be possible that the period depends on the state. If you have a disconnected graph, you can have one part which is bipartite, other part which is not bipartite. Then this side the periods will be 1, that side periods will be 2. That can happen. But if the chain is irreducible, then all the periods are same. It's a very good question. Yes. But since I am going to assume irreducible and aperiodic, I glossed over it. So I must point out here that if any of you have taken a course in Markov chain, usually you come to this theorem after much longer, and there is a lot of time wasted on some all sorts of classification of a Markov chain. There is no point to it. Most Markov chains we see will be irreducible. Sometimes they won't be aperiodic, but aperiodic is a natural assumption to make. Aperiodicity is a very irritating assumption. I mean, periodicity would be a very irritating phenomenon. There are ways to get rid of periodicity. And so, really, it's enough to work with irreducible aperiodic chains for most of the things. That would be interesting enough. Yeah. Any other questions? Was there further question on this?
No, thank you.
Just since you asked, you can also have period 3. I only showed period 2, but you can imagine having period 3. For example, if you have a tripartite structure, so let's say you have some vertices here, and some vertices here, and all the, period 3, if it's a directed one, if all the edges, we have a directed graph like this. All edges from here you can only go to these sets, and from here you can only go here, from here you can only go here, then the period will be 3. Okay, you can only come back in 3 steps or 6 steps or 9 steps and so on. So that period can be 3. Yes. Okay, so then let me go forward. So we have almost solved completely, we have solved the question of long-term behavior. So one question I would like to discuss is, what is this pi? By pi, I mean this numbers pi j in S. So we are assuming, so we are taking for an aperiodic, for an irreducible aperiodic chain. Okay, so what is this pi? How do I compute it? Okay, how to compute it? What is pi? How to calculate? Okay, we actually already got a formula for it. So let's use it, but I would like to explain a bit what it is. Answer, we saw that this pi sub j is nothing but you take the x inverse 1 comma j. So that is pi is the first row of x inverse. Okay, so what is x? So remember that p is in the decomposition x j x inverse. Okay, the Jordan decomposition. Jordan, what is it? Jordan canonical form. Okay, so let me just show where we had that. Yeah, so if you write P as xj x inverse, then it is the first row of x inverse that will give you the pi. Now, what is the first column of x? We saw first column of x is in fact the eigenvector of P corresponding to eigenvalue 1, right? The first eigenvalue is 1 and the first column of x is that eigenvalue. In fact, if you just look at it, so let's just use that idea. So then P dagger or P transpose I like this. What is P transpose? It is X transpose inverse or X inverse transpose. Either way you can write X inverse transpose J transpose X transpose. From this, what you can check is that the X inverse transpose, maybe, yeah. So from this, one can see that what is the first row, the first pi is first column of X inverse transpose, right? You can see that it's the first column of X inverse transpose. But then what does it mean? Hence, pi is the eigenvector of P transpose for eigenvalue 1. Right? So when I wrote P as xj x inverse, you agreed that and j has the first eigenvalue is 1, which is a simple eigenvalue. You agreed that the first column of x is the eigenvector corresponding to eigenvalue 1, so it is just 1 1 1 1 1, right? So the same for P transpose, it looks like this. The first column of this x inverse, which is the same as first row of x inverse, first column of x inverse transpose, which is the same as first row of x inverse, should be the eigenvector of P transpose for the eigenvalue 1. And that is the description of the, so this pi. This pi is actually, so if P has eigenvalue 1, P transpose also has eigenvalue 1. Okay, the eigenvalues of P and P transpose are the same with multiplicities, with the same multiplicities. So P transpose has also eigenvalue 1 with multiplicity 1, and pi is just the eigenvector of P transpose for the eigenvalue 1. Okay, that's it. So that is what it is. Still, it is a pain to calculate eigenvectors. It's on a numerically you can calculate on a computer. There are very good algorithms to calculate the first eigenvector maybe, but still it doesn't give you a simple formula for pi. By just looking at p, can I write down what is pi? So that is a little complicated. So this tells you how to calculate it. So what tells us how to compute pi? From p. But it is not easy. It is not easy in general because you have to solve that eigenvalue equation. In other words, there is a linear system you have to solve. Need to solve multiplied by pi equal to pi. We have to solve this equation. And you remember also, this is a point in the Perrin-Frobenius theorem that the eigenvector corresponding to the largest eigenvalue has positive entries. So this pi will have positive entries, right? Or non-negative entries. No, it's positive entries actually. So this is possible, but it is still not always easy. And indeed, in general, we are not able to find the pi very explicitly. But there are two really simple situations where we can find pi. Okay, two situations, and in fact, these are the only situations where we usually can find. Okay, two situations explicitly. Okay, first one. See, what is the eigenvalue for P corresponding to the eigenvalue 1? It is the constant vector 1, 1, 1, 1, 1. Why is that not the case for P transpose? Why is 1, 1, 1, 1, 1 not the eigenvector? Shouldn't it be the eigenvector of P transpose? And if not, why not? Anybody? Should 1111 be the eigenvector of P transpose also in general or not?
If column sum is 1, then it will happen.
Exactly. So because column sums are not necessarily 1. So even take a two-state Markov chain, the column sum. So if I go back to an example of a two-state Markov chain, let's say two-state Markov chain, the row sums alpha and 1 minus alpha add to 1, 1 minus beta and beta add to 1, but there is no guarantee that alpha and 1 minus beta has to add to 1. So when we do transpose, the row sums are not 1, right? But suppose they are. In many situations, they are. Well, okay. If it so happens, if P is what is called doubly stochastic, that is, row sums are already 1, but row and column sums are 1. Then P transpose multiplied by 1 equal to 1. Okay. But of course, pi j's, I had to say something. Pi is the first eigenvector, but eigenvector is defined only up to a multiple, whereas pi j's add up to 1. Okay. Why do pi j's add up to 1? I took, so therefore, let me say pi j is uniform 1 over n for all j in S. Okay, so that is pi is uniform. See, pi, why should the pi j's add up to 1? You can see it from the fact that the way we normalize, so the Jordan canonical form when we rotate, I mean, there are different ways to explain this. When I wrote xj x inverse, I took x, the first column, to be 1, 1, 1, 1, 1. I could have taken it to be any constant because any constant vector is eigenvector. But when you apply x inverse, when I change x inverse will also change. So if you just look at the equation x inverse x should give you identity, then you will see that the first row of x inverse, if you take the column sum of first row of x inverse, if you add up x inverse x, the 1 1 entry is just the first row sum of x inverse, and that has to be 1. So that's one way to say pi j's have to add up to 1. But let me, in the interest of time, let me just leave that. Pi j's, another way to think is pi j's are probabilities which should add up to 1. So either way, it should be 1 by n, where n is the size of the state space. This happens in many situations. We'll give examples in a moment. But second one, this is one situation where many times it happens. So another situation is if we can guess numbers sigma I positive numbers such that sigma I in S. Okay, suppose I can guess numbers such that sigma I Pij equal to sigma j Pji for all I and j in S. Okay, then we say that the Markov chain is reversible with respect to sigma. This has some deeper meaning, but for me here, it is mainly a tool for finding stationary distribution. Okay, but okay, this is a definition. If you can find positive numbers such that sigma I Pij equal to sigma j Pji, okay, how this will come, we will see examples. But point is, then what I want to say is that pi I is just this sigma i's. Pi j is just sigma j. Just normalize it. If you normalize, if you find such sigmas, then you normalize them, you will get your pi. Okay? Reason, let's give a proof. It's very easy. So I want to say that you look at P transpose sigma sub j. Okay, what is that? It is P transpose I comma j sigma, P transpose sigma sub, let's write as I. P transpose sigma I is P transpose ij sigma j, sum over j. Okay, but what is that? P transpose ij is Pji, right? P transpose ij is Pji entry. But what is the assumption? Sigma j Pji is same as sigma I Pij. Okay, so this becomes sum over j in S of sigma j Pji. I can also write as sigma I Pij. Okay, but this is remarkably, now the sum is over j, right? So sigma I comes out. And what is the sum of Pij over j? That is 1. Sigma I Pij, the sum over j is 1 because row sums of P are 1. So what this shows is that P transpose sigma is sigma. That is, sigma is an eigenvector with eigenvalue 1. And pi is just a multiple of sigma. So pi is also an eigenvector. Of eigenvalue 1, a vector of P transpose of eigenvalue 1, and it also has the property that sum of pi j is 1. So that's why that is the answer. Okay. So this is a somewhat mysterious one if we have never seen. The first one is a bit more natural. If P is, for example, if P is a symmetric matrix, then because if row sums are 1, column sums also will be 1. Or even if it's not symmetric, but if column sums are 1, then pi j is 1 by n, that's easy. But this is somewhat more mysterious, that it says if we can guess number sigma I such that sigma I Pij is sigma j Pji for all pairs I and j, then that sigma will automatically become the first eigenvector of P transpose. And so that will give me the stationary, this pi is called the stationary distribution. Okay, I should have said that. Pi is called stationary distribution of the Markov chain. Okay, stationary distribution of the Markov chain. And what we are saying is that there are two situations where we can find stationary distribution, these two. Okay, so let's go for some examples and see that we can calculate it. So yeah, in the remaining time, maybe I will just do that. But any questions about these two? I mean, maybe the second one will be clear when we see examples. So let's take one example, which is simple random walk on a graph. Okay, so let's take a graph like this. So what are the pi's? That is the question. Okay. So is it true that, so we need to find, goal is to find pi. Okay, for this simple random walk on the graph, we need to find pi. So let's check. You have to directly either solve the eigenvalue equation, which is always a pain. Otherwise, if it falls in one of these two situations, we can guess. Okay, so let's see. Is the first condition satisfied? Is P doubly stochastic? I don't think of only this example. Is P doubly stochastic? That means are the column sums necessarily 1? So you remember what is Pij in this case? Pij is 1 over degree of I if j is adjacent to I and 0 otherwise. Okay, 1 over the degree of I if j is adjacent to I, and so if I add the column sums, means I sum over I in S, Pij, which is the sum of 1 over degree of I over I in S. Will that give me 1? I mean, sorry, not 1 over degree. Sorry, this will give me, what will it give me? Sorry. So what will this give me? It will give me sum over I adjacent to j. Only I adjacent to j will give me 1 over degree of I. So in other words, to j, you take all the neighbors and calculate reciprocal of the degree and add it up. Will that give me 1 usually? For example, take j to be this. It has one neighbor whose reciprocal degree is 1 by 3. So that's not going to give me 1, right? So is there some situation where P becomes doubly stochastic? Can you imagine a situation where...
Regular graph.
Exactly. If P is regular, if G is regular, if G is deregular, then P is, you remember, 1 over D times the adjacency matrix. Okay, this is the adjacency matrix. Is in fact symmetric. Hence, column sums are... Okay, why is this handwriting going on? Column sums are 1.
So here we have to care about that aperiodic thing also, not bipartite.
Yeah, you are right. Well, okay. I am kind of glossing over that point. You are right. No, okay, let's separate that issue. If it's not aperiodic, you cannot apply this theorem directly. Okay, but the calculation of pi is still a question. What is an eigenvector with eigenvalue 1 for P transpose? And the answer is given by this. Uh, so, so if G is deregular, then it will be uniform. Okay. Yeah, your question is valid. To apply the theorem, I need irreducible and aperiodic, and bipartite graph may be aperiodic, but let's separate the two questions. Finding the pi means just finding the eigenvector with eigenvalue 1 for P transpose. And that is what we are talking about. So what about in general? We cannot, in general, it is not like that. It is not, column sums are not 1. So we will try 2. In general, we try to. We show that the chain is reversible. Okay. So that is want to guess sigma I in the vertex set such that sigma I Pij should be equal to sigma j Pji for all I comma j in S. Okay, this has to happen for all pairs of vertices. Now, if I not equal to j, this is satisfied. Okay, sorry, not for I not adjacent to j. For I not adjacent to j, both sides are 0. Okay, for I adjacent to j, we get sigma I divided by what is Pij will be degree of I. And this side we will have sigma j divided by degree of j. So can we choose the number sigma I so that sigma I by degree I equal to sigma j by degree j for all I and j? Can we do that? What is our guess then for sigma I? What can I take sigma I to be so that this equation is satisfied? Yeah, any guess for sigma I? See, I'm saying how to guess this sigma I. I want to guess sigma I so that sigma I Pij, sigma j Pji. In the case of simple random walk on a graph, for I not adjacent to j, both sides are 0, so equality is true. For I adjacent to j, I need this equality. Sigma I by degree I should be equal to sigma j by degree j. What is a natural number, natural example of sigma I which will make this happen?
Sigma I equal to degree I.
Yeah, so that's the most obvious, right? Just take sigma I to be degree I, so both sides become 1. So guess is sigma I equal to degree I. That will satisfy. Okay, so that means, so what is the conclusion then? Then the stationary distribution is given by pi I. For every vertex, pi I is proportional to the degree of y. We have to sum it by, we have to normalize it so that the sum is 1. This is just a normalization factor so that pi I is add up to 1. So pi I is just proportional to the degree. And in fact, we saw this yesterday when I showed you simulations of a graph. The proportion of time spent in different vertices was proportional to the degrees. Right? The higher the degree, the more time it spends. So this is now completely proved and captured by this fact that pi I is in fact the degree of the vertex, proportional to the degrees of the vertices. Okay, so if a degree, something has degree 2 and another vertex has degree 3, you spend 1.5 times time more you visit the second vertex than the first vertex. So this is an example of a reversible Markov chain. Okay, any questions on this? Okay, let me do one more example, that of the Ehrenfest chain, because that is an interesting example also. And I will end with that. Second one is the Ehrenfest chain. Where the state space is 0, 1, 2 up to n. Okay, n is, we had this idea that we have gas molecules with a, some gas molecules are there and there are gas molecules. One of them will be picked and moved to the other side. So I will just write here what is Pi. Pij equal to, if j is I minus 1, the probability is I divided by n, and if j is I plus 1, then the probability to move is n minus I divided by n, and it is 0 otherwise. If j is not I plus 1 or I minus 1, the probabilities are this. Now, what is the stationary distribution? Okay, so again, try to guess. So, want to guess. Sigma I for states such that sigma I Pij equal to sigma j Pji. Okay, for all I and j. Now, if so this is easily satisfied if I minus j is, if I not equal to, if I and j don't differ by 1, both sides are 0. Okay. So, for if I minus j is 1, so we can just look at sigma I Pi I plus 1 equal to sigma I plus 1 Pi plus 1 I. This is what we want. Okay. In other words, let's write down what that is. Sigma I into I to I plus 1, the probability is I by n. And we want sigma I plus 1. Here, this is n minus. So if you just plug in these values, you will get that this equation has to be satisfied. Okay. If I leave you to guess, you will do it. It will take 10 minutes or 20 minutes maybe to guess what are these. So what I'll just tell you, check that sigma I equal to n choose I satisfies this. If you take n choose I, sigma I plus 1 by sigma I will be n choose I plus 1 by n choose I. You can cancel everything. You will see it will come out to be the same. So that means pi I have to normalize this sigma I, which becomes the sum of those things is 1 by 2 is 2 to the n by the binomial theorem. So sigma I, pi I is exactly this binomial distribution, which is what we saw in some simulations yesterday. Okay, so it will look like it is mostly concentrated near the middle. It looks like this. So near n by 2, the highest chance is near n by 2, and properties of binomial distribution will tell you that this will, yeah. Anyway, so I will leave it at that, but you can calculate the exact stationary distribution of the Herrenfest chain because you can guess the sigma. When you cannot guess sigma and when you don't have a doubly stochastic matrix, it's very difficult to find pi. You may have a theorem which says it exists, but it's hard to find it. Okay. Okay, I will, yeah, I didn't give the extra time to ask questions, but I will stop here.
Manjunath,
Yes.
why it is called reversible to justify?
Right, reversible means it is, it has to do with the reversibility of the chain. But it's what it means is that, okay, so, yeah, so the thing is, if the chain is, so if you are shown a video of the chain, okay, or the reversal of the video, you will not be able to tell which is the original and which is the reversal. Okay. Why? I mean, so, but that has to be a bit more, made a bit more precise. You have to start in stationarity. So this is something that is there in physics. We hear often that if you are shown a bunch of molecules moving or a bunch of billiard balls hitting each other, so there is a video. And suppose you time reverse the video and show the video. That is also perfectly valid, meaning that that is following the laws of physics. You cannot tell which is the original and which is the reverse. So if the Markov chain has this property, and the caveat is that you have to start in stationarity, not start at a particular vertex, but suppose I pick a point according to the distribution pi and then run the chain forwards, and then also take that chain and show the video backwards. You cannot distinguish between the two of them. That is what reversibility is.
Okay.
That is, I mean, strictly what I'm saying is that if I take a trajectory, so let's just write here, pi I0, p I0 I1, p I1 I2, dot, 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 let's say p I7 I8. Suppose I run the Markov chain for I steps. So if you use the reversibility, what you can see, pi I0 p I0 I1 will become, you can change it to p I1 I0 into pi I1. Then pi I1 p I1 I2, you can change it to p I2 I1 into pi I8. So this is the probability of the reverse trajectory, where you start at I8, go to I7, then I6, I7, I0. This is the reverse trajectory, and this is the forward trajectory. They have the same probabilities. Yeah.
Okay. Thank you.
Okay. Yeah. So what I plan to do, I mean, just to say one word. So I had announced some two things, so I won't have time for that. So I will skip one of the things and just maybe stick to Markov chains and in the last lecture. Okay. I'll skip that Lindstrom lemma and Carlin McGregor.
Okay. Stop
Okay.
recording.